say that. Sorry.
Right, I know, I interrupted.
No, that's okay. That's okay. Take one of those and pass them around, please. Bring this up.
I was hoping you were gonna print those.
Okay, guys, so any other assignments are due 3 minutes ago. So if you have it, give it up now or forever hold on to peace. Alright, so what I wanted to do today was I wanted to go through and start talking about digital logic circuits and different number bases. And I think that we also had one more example to do with the rules of inference as well. So let me pull that up as well so that way we can finish that up. Because I think I'm going to ask for you guys to submit that on the next assignment. Let me do that. So I think we did the first one, correct? And we just didn't do the second one. Okay. So sorry, it's been a week and I forgot where we were with regard to that. So I'll get there with that. Okay. That's what, no. Okay. So let me copy this down real quick while you guys are still getting the worksheets. Not W. Yes, sir.
Did you need to hand out 2 different sets of rules?
Yeah, cause I got.
Or
I
do
actually
we
had
only
those
supposed
for
to have
two, I
one?
thought it was just
Oh,
one.
what else do you
We've
have?
got this one.
Oh, statistics stuff.
Found that one.
Measures of central tendency.
Yeah, that's statistics. Just hand me back the statistics stuff. Sorry about that. I didn't realize that they were lumped together. I just got it back from the copy center. I was wondering where those were.
Has them up in front and center.
Sorry about that.
Digital logic.
Circuits.
That's fine. Yeah, if you guys want, just pass all the extra stuff up and whatever, or you just pass it down at the end. I don't care. So I actually made extra copies of them this morning because I couldn't find them and they were just lumped in with all the other stuff. Okay. Okay, guys. So let's go ahead and see if we can do this other example of showing that an argument form is either valid or invalid, and we're going to use those rules of inference. Okay. So go ahead and bring back up that worksheet that has the rules of inference at the bottom. All right, I'll try to bring it up on the screen so that way you have it. It's the one that has the Boolean logic laws on it. Okay. So these are basically like our 8 rules that we can utilize. Remember what we're trying to do is we're trying to put together some sort of, I guess, I wouldn't say roadmap, but we're trying to put together like an algorithm, if you would, that's going to lead us to the conclusion. Okay? So I think that's last time what I suggested was you always start with the most simplistic possible statement that you have and then try to work from there. Okay? So to me it looks like not W is the most simplistic statement. So we're going to start with this, okay, just because it only has a singular statement in there. And then what we want to do is we want to look at something else that might have a W in it. Okay? So always start with whatever has just one term in it or one statement. And then it looks like to me that the only thing that's possible that has one statement is U or W. Okay? So let's see if we can build one of those 8 basic rules of inference, maybe just using these 2 statements. Okay? So does somebody think they might be able to put together a statement and then come up with a conclusion from that argument form? So, go ahead, sir.
So U or W, and then not W, so you got U.
Okay, so we would have U or W. That's given. Not W is also given. And therefore you ended up with U, correct, sir?
Yes.
Okay. Now, what was one of the 8 reasons that you were able to give that, sir? Elimination.
Elimination.
Elimination. Good. Okay. So this is valid by the elimination property. Okay? So make sure when you guys are doing this, you justify your steps. Okay? So that's the elimination step. All right. Once we're done with that, what we can do is we can usually just cross these off, and then we can look for something else that might have a U in it. Okay? So it looks like that the only thing that might have a U in it is the third statement form. Okay? So does somebody think they might be able to use what we just got in step 1, as well as something else in the given information, to try to come up with something conclusion or some conclusion for the next step?
So U implies not P.
Okay, so we have U implies not P. Yes, sir?
So not P.
Not P.
Not P implies RNS.
Well, we don't want to use, we don't necessarily know not P yet. Okay, so we can't use that. So, suggestion, sir?
Could you do like U therefore not P?
So we could say, we have U from step 2, therefore, not P. Okay? All right, the first step was given. The second is a result of step 1. We just showed that's true because we know that all those rules of inference are indeed valid. Okay, so U implies not P. U is valid by step 1. And then which of the 8 rules is going to be able to enable us to go and say that this statement or this argument
Modus
form is valid?
ponens.
Modus ponens. Very good. Okay. Okay. So does that make sense, guys? All we're trying to do is we're just trying to build something that looks like those basic rules of inference. Okay? We can cross out U implies P now, or U implies not P. And now, at this point, we have U and not P to work with, okay? So does somebody think they might know a next step that we can utilize to be able to try to continue with this?
Not P. The not P implies RNS.
So we have not P implies R and
Not S. Sorry.
Okay, that's okay. Okay, so I like using that one, okay? And then what else could we use from there? Or what else could we do? Yeah, we could use not P, and we had not P from step number 2, right, Don? Good.
Yep.
So it's going to be not P from step 2. And then what's that going to result in, and why?
R and S.
R and not S.
R and not,
That's
not S.
okay.
Sorry.
Good. So R and not S. And why are we allowed to say that we can conclude R and not S?
Modus ponens.
Yeah, modus ponens again, okay? There's no law saying that we can't reuse the same laws, okay? So this is valid by modus ponens. Okay, good. All right, we can cross this one off. Now remember, we're trying to get to not T, okay? That's the conclusion. So now what we have is we have both R and not S at our disposal, okay? So I think we're basically 2 steps away from being able to get to the answer to this, or to the not T that we need, okay? So, for step 4, okay, if I look at T implies S, which is the only premise that we have left, excuse me, wouldn't I want to use something with an S in it?
Mm-hmm.
So from step 3, I'm given R and not S, okay, that's step 3. Well, what can I say that might be useful as a result of having both R and not S? Sir?
Implies not S.
Yeah, because it's going to be the specialization, right? We just choose one of the 2, okay? If I have, I don't know, blue marker and black marker, I have them both. So I just pick the marker that I want to use. So this is going to be valid, not S, or therefore not S, by the specialization rule. Okay. So, and the reason we knew to use not, or that we knew not S was going to be useful, is because there's no R in any of the other premises, right? You just want to pick the one that we need from this. Okay? So if you have an and, you can do that. You can't do that with an or. Okay? And then finally, for step 5, I think we can finish this off. So does somebody think they might be able to get to the conclusion given the information that we have thus far? So, go ahead, sir, please.
Can you use Curtis Collins, say T implies S,
Yes, sir.
not S, therefore T.
Perfect, thank you, sir. Therefore, not T. So not S was for, that's okay, you're fine. Don't worry about it. I knew you'd write it as that. From step 4, you had not S. And then as a result of modus ponens this time. Okay.
Told him.
Oh, told, I'm sorry, that's right, we used ponens in the other ones. I apologize, I got the first word right. But as a result of modus tollens this time, then we get to not T. Okay? Alright, so this is exactly what I would ask you guys to do for homework. Okay, so this is like those last 2 problems that were on assignment 1. So you guys will just hand those in on, I guess, next week when you guys submit the assignment. Okay, I think the next assignment is going to be due next Wednesday. Okay, so that way you guys have a few days to work on that stuff and also ask me some questions.
On the 14th?
One more time, sir?
On the 14th?
Yeah, today's the 7th, so yeah, the 14th. Okay, I'll post it in Blackboard, so I just haven't thought that far in advance. So. Okay. All right. Questions I can answer, guys, about this. Okay. Usually, what I do on the first examination, I give you guys a question just like this. It's worth 10 points. Okay. So make sure you guys go back. If you don't understand it, make sure you guys come and see me so I can help you. Okay. So the next section that we're going to take a look at is we're going to start taking a look at the circuits, the digital logic circuits, and different number bases. Most students do very well with this stuff. Okay, so remember we just talked about truth tables, we talked about truth values, inputs, and outputs. Okay, one of the applications of that is something called a digital logic circuit. Okay, every computer is comprised of billions of circuits, and when it comes down to the core, every computer circuit is designed with either an and, an or a not, or several of those can join together. Okay? Some of you guys might have worked on breadboards, some of you guys might have done some computer architecture where you actually program those sorts of things in, and you might put like the different conductors together, the logic gates together to be able to figure something out like that. Some of you guys may have not done that. Okay? So I don't really care if you have or haven't, doesn't matter. All we're going to do in this class is just look at those. Okay? So, with a digital logic circuit, okay, once a signal goes through it, you can't reuse the signal. In other words, you can't backtrack a signal, okay? A signal's one way. You can loop it back around if you wanted to for some reason, like if you wanted to do this, but that wouldn't be smart because then you never really have an output. You just have you just have basically an infinite loop, and that's not going to do anything for you, okay? So when I say that there's only one output, what I mean by that is that once it goes out, it shouldn't be going back into the same circuit for any reason. Okay? Alright, there's only a finite number of inputs. And that's just because if there were an infinite number of inputs, that means there's an infinite number of material. That doesn't matter. Okay? The only possible inputs are true and false. Okay? You can't have like a 2 being pushed through here. When we start talking about digital logic circuits, instead of true, we use 1, which means valid. And then for those of you guys that know computer science, 1 is like the Boolean true, and then 0 is the Boolean false. Okay, so that's basically the inputs that we're going to be putting through this. Okay, so does that make sense, guys? The only things that go through circuits are 1s and 0s, nothing else. No cats, no dogs, no lawnmowers. All right. So one of the most basic things that we have to do is we have to make sure that if I give you a circuit, you know all the different combinations and permutations that can come out of that circuit. Okay, that's basically fundamental to this. Okay, so we have this circuit, and the first thing I want to do is I just want to make an input-output table for this circuit. Okay, when I say input-output table, it's the same thing as a truth table. Okay, so here's what we're going to do. We're going to have a P. We're going to have a Q. Because we have a P and a Q, how many rows are we going to have for this input-output table? 4, right guys? 2 to the 4, or 2 squared is 4, okay? And basically, remember how we did true, true, false, false, true, false, true, false? Well, now what we're going to do is we're going to do 1, 1, 0, 0, 1, 0, 1, 0. Okay? If you want to use T's and F's, that's fine for me, okay? But if some of your teachers might not like T's and F's, if you're in computer classes, they might want ones and zeros, okay? So just don't use T's and F's, make sure you ask your teacher, okay? I know the difference, but they might not. Okay, so here's what we're going to do, guys. We're going to have an output for this. So we have two trues going through there, okay? So here's the way that I think about this, okay? Let's say I run 2 1s through that table, okay? Notice that this P right here just kind of carries down. In fact, let me do this. Let me put the 1s at the beginning. Not that it matters that much, but... So there's 2 1s that are being run. So in other words, whoever's running the circuit turns on the impulses, okay? So there's 2 electrical impulses that are going through there at the same time. This 1 actually traces down to here. So all we're going to do is we're just going to figure out what's going to happen. Okay? If I throw a 1 and a 1 through a gate, what's the output of 1 and 1?
1.
1, right guys? If it's true and true, just like you guys did with Boolean stuff, okay, or when we did with the truth tables, it's a 1. Okay? What happens if I run a 1 or a 1 through this?
1.
That's a 1 as well, right? Remember, the only time an or a disjunction is false is when you have both zeros. What happens when you run a 1 through a not? It's a 0, right? So basically what we're saying is that if I run 2 1s through that gate, in other words, I turn both impulses on, the output is a 0. Does that make sense, guys? We're just basically tracing it, and we're using the tables that we already know. Okay, that's all we're doing with this. Okay, now what I'm going to do, okay, I'm going to erase this stuff, okay, where you guys can just scratch it out, whatever, okay. Now I'm going to throw the second permutation through. So I'm going to turn on the P impulse, but I'm going to turn off the Q impulse, okay. P still traces down, so this is a 1. Okay. So what happens when you run a 1 and a 0 through an AND?
0.
That's a 0, right? If you run 0 or 1 through here, that's a 1, and then a 1 through a not is a 0. So it looks like that, so far, all the impulses